Very good. I think we can get started. We have 22 people online. And compared to that, we can have in person. So today we'll have Jun presenting his work on fleet management and then its fleet's interaction with the grid if we have electric vehicles in the fleet. Jun is a PhD student in integrated systems engineering, ISC department, and a lot of operations research that happens in ISC that he brought up with the electric vehicle topics that we look into it. So we essentially merged the two topics, hence his PhD work came out of it. He will be defending his final defense or final PhD next week. So this is a good opportunity for him to rehearse what he will be presenting. So ask him good questions and prep him well for the exam.
Thank you for your introduction. And so the today's topic, which I named as charging infrastructure management for enhanced grid resilience, but it is not only related to grid resilience, but we also cover the overall overall research topic throughout my PhD. So I would like to first start with brief introduction of fleet electrification. So the fleet electrification, from my own definition, it's a kind of replacement from conventional vehicles to electric vehicles. And undoubtedly, it's a trending topic, but it's also a complex matter since there are so many factors that we need to consider in high initial cost. And according to one survey, there are lots of concerns regarding charging parts from the fleet owners. And actually from the statistic, we can see why the entire automotive market fluctuated over time, the electric vehicle market steadily increasing. But at this time, I'm not sure whether this is true for now, because as we can see, for now, the Tesla stock situation for today is like this. And I'm not sure whether this trend will continue, but I'm sure in the long term, this EV adoption will increase at the end. So around this fleet electrification topic, depending on my background, departmental background, I'm mostly working on operations research side and try to see this as an OR problem. And operations research basically includes management problem and problem modeling with optimization techniques to come up with decision making. And by combining these two sectors, we can define this as an electrified fleet management problem, which to optimize the topics around electric vehicles and should include charging infrastructure and charging or route scheduling or initial investment or purchase cost. And this can be more detailed, like the route optimization problem or charging infrastructure optimization problem, also with fleet composition and its management, also with charging or route scheduling problems. So centered around electric vehicle implementation with both operational management side, I divided this into 4 different subtopics. The first one, electric fleet route planning problems, which includes fleet composition and route planning, energy cost analysis. And for EV operation, recharging planning should be considered associated with cost and charging time and uncertainties and availabilities of the charging stations. And since we are dealing with vehicle itself, we need to consider these vehicle dynamics definitely. And the final one, which is the grid resilience, is another factor that I would like to focus on. This is because electric vehicles should be supported by enough sufficient grid because these the energy main energy source for EVs are electricity. For sure, we need to consider this once we are considering large size fleet. So for these topics, I designed this with three major topics throughout my PhD, and the third one might be our main focus for today's seminar. But I would like to also cover the first two topics to cover my entire research interest. And all this research has been published with few journal and conference papers of it. So starting from the first topic, which is fleet and infrastructure aware energy efficient routing. This is primarily the fleet routing problem, which covers we need to there are a number of pickup and delivery locations that we need to service, and while keeping those constraints, we want to minimize fuel consumption or time or overall operational expenses. And meanwhile, we would like to also consider different vehicle technologies as an option as well. Not only consider EV as a fleet operation, but we can consider ICE and HEVs as other options. This is because for each vehicle technology has its own strengths and has its own characteristics. So depending on situation or route situation, in some cases, the other technologies might have more benefit. So the ultimate goal of this topic is to come up with proper route planning with its composition, also with recharging planning. So to reach out this point, I divided this into three processes. We first start from the data pre-process, since I'm trying to targeting more practical research based on actual data. And this goes into point-to-point routing problem to come up with accurate energy consumption values or proper path planning. And finally, we can go into the fleet routing problem, which can be defined as pickup and delivery problem. So for the first part of this research, which is the data pre-process, we should collect the data, and our research interest is in Columbus, Ohio area. And once we make this as a graph network, then it can be structured with 77,000 node information and 171,000 link information, along with different attributes. And once we have this network, then we can first solve the point-to-point routing problem based on load equation and its speaker specification and its efficiency. And the goal of this point-to-point routing problem is not only come up with what are the specific path planning from one point to the other point, but by the combination of all these information, we can the preparation step to move before the fleet routing problem. So once we have all these data preparation and these preparation steps, then there are two different objective functions for fleet routing problem. One is energy minimization, whether to minimize the total fleet energy consumption. The other one is total cost of ownership minimization, which includes vehicle purchase cost, fuel cost for maintenance and repair costs, and taxes and insurance. So depending on these two different objective functions, I can model this based on mathematical formulation. I will not go over this in detail, but the main goal of this formulation or problem methodology is to come up with what's the fleet composition, proper fleet composition, along with its route planning, also with recharging planning, while minimizing fleet energy or fleet total cost of ownership. And one of the main limitations of this approach, which based on mathematical formulation, is that academically this is categorized as the NP-hard problem, which cannot be solved within a polynomial time as the problem size increases. So that's why it has some nature limitation to apply this with a large size problem, and we need to come up with some alternative or approximated algorithm or approach. That is another algorithm that I propose based on predictive algorithm, which is simulated learning one. And I made some modification based on simulated learning algorithm, like adding some concepts and divide it into two phases. And then finally, we can use this algorithm for the large size problem. And once we apply this algorithm and problem and try to solve this with some key studies, and we can basically compare like what are the differences between total cost of ownership minimization and energy cost minimization results based on like what are the fleet, how the fleet composition and its route planning different. And also once we more generalize this with more experimental sets, and we can have some more like general insights like what are the deeper preference depending on objective function of operation here. Like for energy minimization case, for sure, BEVs are the most preferable option, but like in terms of TCO minimization, ICBs and HCB might be more preferred compared to BEV, but the degree of preference might be a bit different depending on the operation year. So that was pretty like quick overview of this first topic. So here I'd like to cover the fleet routing problems with two different objective functions. One is the energy minimization, the other one is the total cost of ownership minimization. And for each objective function, we can come up with some insight and interpretation. And also we can see how the charging options bring the benefit throughout the overall experience. So this was the first chapter. And as an expansion from the first chapter, the second topic is the time varying and capacity fleet routing problem. So here, in the previous chapter, previous problem, the problem was solved under the deterministic environment. So all the factors and the situations were fixed and static. But in real world, as you know, like there are lots of stochastics and the dynamic components around us, like we can see like peaker breakdown, or sometimes there are load costs and there are no available chargers and traffic congestion. These are like stochastic and dynamic factors that we need to consider once we try to solve like fleet routing problems. So in this second topic, in this research, I'd like to see consider these kind of stochastic dynamic environment, like a time varying features from the traffic and charging speed varies within the location and uncertainties for charging station availability, specifically for like with waiting time. And I will mainly focus on scheduling the charging station, route selection, where more on time. So for the modeling of uncertainties on waiting time at the charging station, this should be basically modeled on the top of queuing theory. So in this queuing theory, there should be basically a few specifications that we need to consider, which is number of chargers and charging power at the charging station. And by using those as an input information, we can come up with we can model this as a stochastic formulation, like what's the utilization level and what's the average waiting time for the charging station. These are all inputs that we can use. The other feature that I would like to consider is the time varying feature, especially depending on time dependent or traffic dependent feature. As you know, as you're familiar, like traffic speed and travel speed or travel time is not constant or stable. It highly depends on time of the day. Like if we drive on the rush hour, the travel speed is very low, but once we drive on the peak time, then we can drive pretty much faster. So this should be reflected in the like routing problems as well. So first, what I did here is first discretize and made all these different scenarios depending on time of the day as a different information, like what are the expected time and expected energy consumption, expected driving distance, and on the simulator, depending on the exact time at time of the drive, we can bring the proper like scenario. So once you compare like this kind of scenario, like driving at 8 a.m. or 8 p.m. or peak traffic situation, we can see not only the travel time and energy consumptions are different, the route visual path planning is also affected by this time of the day scenario. So by incorporating all these factors that I introduced, now I'd like to introduce some charging planning algorithms. So basically, I would like to consider like charger availability, which is a waiting time at the charging station, and charger specification and traffic time as when we are selecting charging stations. So basically, there are two approaches, two models that I implemented. One is a full mathematical formulation based one, the other one is the simplified version. And the reason of this simplified version is because in the full math formulation, this includes nonlinear functions inside. So it's pretty hard to use in in the large size problem or practically. So that's why I come up with this kind of simplified version. And by applying this one, we can see how this charging selection depends on like ovarian time situation or the time that we have. So basically, if you consider not ovarian time at all, it will always prioritize the charging station which might be cost-effective ones, which have like a lower charging time, lower charging speed, and less number of chargers. But once we consider this adaptively, if we have like a limited travel time or limited given time, then at some times we need to more prioritize on like charging stations which provide faster charging, like up to like a 300 DC fast charging. But if we once we have some like sufficient time for travel or drive, and we can more focus on cost-effective ones. So that was the main like motivation on and the main like target of this algorithm in this research. And for by comparing like the total time and like the cost, even operating cost, the adaptive one shows like a superior and like non-aware algorithm. So that was the another second. That was the short overview of the second topic. So in the second topic here, I'd like to see like how the I would like to incorporate the real world uncertainty and try to see cost and time savings and like charting decisions inside and significance of temporal vectors, especially like traffic has factors inside. So up to here, it's a pretty fast overview and covers of my research topics. So I'd like to more focus on this third topic, which is the main seminar topic today. So the third one, which optimizing. And by the way, if you have any like questions on the first two chapters or first two parts, then feel free to like ask me or and reference papers from my published papers as well. But for today's seminar, I would like to more weigh on this third topic, which is optimizing charging infrastructure management for enhanced grid resilience. So I'd like to start from this introduction again. So as I shared, EV adoption increases and the electricity demand in transportation is also rising. So maybe before until like 2019-18, the most of the electricity demand came from like industrial or residential or commercial sectors. But maybe after like 2019, the electricity demand from transportation sector is also increasing or aligning with the EV adoption. So by aligning this trend, there are like lots of projects and research to consider this EV adoption and to consider this big operation incorporate with grid impact. So one of the projects from Idaho National Laboratory is to come up with pretty comprehensive platform to measure the impact of transportation sector for grid. The other research like this one tries to measure like depending on the scenario penetration of EVs, like how these impact on grid and what are the charging demand throughout over time. So before I go into grid part more detail, I'd like to give a very brief overview of this power system. So as you know, there are like multiple sequences from the fuel to end users to get electricity, and like starting from fuel to power plants, this electricity goes to transmission. And for transmission, there are like regional transmission organizations, which so-called RTOs, and these RTOs located depending on throughout the U.S. and the region that we are located in is included in Mid-Atlantic. So in our case, PJM interconnection is the main RTO. And after this goes from transmission to distribution, as you may familiar, now this goes to electric utilities like APY is one of them, and there are like other utilities throughout the US depending on the region. So once this from the this distribution is these utilities are the most directly relevant for the from the end user. The other topic that I would like to cover, which from really interesting fact, is that the U.S. electricity was built on mostly from 60 to 70. So they said like today over 70% of the U.S. electricity grid is more than 25 years old. So it's pretty much vulnerable to like storms or catastrophic situations. So at this point, grid resilience matters. Like grid resilience basically is the ability to electrical grid to withstand or recover from disruption while maintaining reliable power. So, but so this, but since we are not a technician or a power supplier, we should approach it with more from the demand side or from the transportation side. So at this point, the one of the topic that we can see is the peak shaving. So the peak shaving is the thing that we can consider from the demand side, which to reduce the demand during periods of high electricity usage to prevent like grid overload and to improve efficiency. So our main focus is starting from this motivation. The main interest from this research topic is to see how to manage grid charging load management by integrating grid side. And this for sure is more valuable in large size fleet because for passenger cars it doesn't matter to consider like grid resilience because it cannot affect at all. But for the large fleet like electric school buses or like the logistic company which has like large fleet, this matters. So but and also it's important to understand like what are the exact energy demand from the fleet to measure this analysis in the integrate. So throughout these motivations, I made this third topic, which is optimizing charging infrastructure management for enhanced grid resilience, into two different subtopics. So in the first phase, I will try to measure like what are the energy and cost footprints based on school bus electrification case study, and based on energy footprint or energy distribution number, now we can come up with like charging schedule to consider grid resilience. So this project basically collaborated with 760 schools. So in the first phase, which to come up with energy footprint or energy distribution, we first need to analyze the fleet operation data, like what are the driving cycles for the fleet and other some background map knowledge information, and also with some basic analysis results. And this will be again will be used as an input for the electrical simulator that we have implemented. And by combining as for the output, then we can move on like a single read analysis, like what are how the SOP changes and what are the like energy consumption profile that we can bring from single reader. By expanding this, we can get like a fleet level analysis results, like entire energy consumption distributional footprint for the school bus fleet. So as you familiar, this simulator based built on like metric simulating associated with like lots of dynamics like HVAC model and powertrain model and battery pack model. And as for the output from this simulator, then we can see like what are the power profile and like energy consumption values and how the SOC changes and what are the based on all these information, what are the like the estimated driving range, and also it's possible to compare like how these electric vehicles different from diesel or gasoline buses. And after we get a comprehensive understanding of the single read analysis part, now we can move on to fleet level analysis. So this first starts from collecting all the data for fleet operation, and so this is the fleet profile throughout the entire group of fleet that we have. And once we later refine it with as a utilization, we can see that the utilization patterns are pretty well aligned with student transportation pattern, like from 6 to 8 a.m., it's the utilization is pretty high, and from 2 to 4 p.m., this is again peaks. And also we know about like what are the driving range and from the what are the driving range or driving range distribution for the fleet that we have, and we know the 42 miles per day is the average number for driving range. So by incorporating all these data and simulator, we can finally come up with energy footprint for the fleet that we have. So basically, it provides some energy distribution that from the fleet that we have, and it's also capable to compare with the gasoline or diesel buses. And also by translating this into MPG values, we can also see these kind of metrics, and we can also validate this from the nominal values that we know from the bus company specification. So from this research, we can see how much energy that we can save transitioning from like gasoline or from diesel buses to electric buses, and how much cost that we can save in terms of operating costs. And we can see like other factors about this research. But up to here, the main focus was on fleet aspects. Like we come up with daily energy footprint with directed school bus fleet, and we come up with like how much we need to expect from fleet charging load. And based on all these preparation, now we can moving on. Like, can we consider like a charging planning or like an infrastructure demand, or moreover like a grid side consideration? So the main research question here now is how many chargers should be installed at the depot to support based on the energy footprint that we divide. And is there any possible plan of charging or install chargers considering grid resilience? This is the other question. And these should be possible throughout the charging plan, proper charging plans for buses and chargers. So as I introduced, now we have like all information about school bus operation and energy footprint. And now we will consider this as another like a charging scheduling problem. So here, there are a few assumptions that I consider. First of all, we will consider all the buses will be charged at depot. So the first research interest is how many chargers do we need at the depot? And we need to come up with what are the proper charging schedule. And finally, once we have all this information, then we can consider like, is it possible to consider grid resilience from the demand side? So this is again formulated with math formulation. And here, the main assumption here is that we are considering overnight charging. So basically, the input of this model formulation is daily energy consumption that we derive from the first grade research and charger specification, and number of days that we would like to consider, and bus specification. And as for the output of this formulation is to come up with number of optimal chargers. But this is not an optimal chargers because it is kind of like a minimal number of chargers to support fleets, electric fleets that we have. And this also comes with charging profile for individual buses and chargers. And also by summing all the like energy demand for individual buses, that we can see like energy demand from the grid is another output that we can see. So as for one example, once we are considering this kind of problem, we are considering overnight charging scenario like 6 p.m. to 5 a.m. And there are like 133 buses, and we are considering operating days as 5 days. And there are like 2 buses can be maximally connected for each charger, and the charging rate is 20 watts. And then once we solve this problem from the formulation, then we can come up with the optimal number of chargers that we need to install, or the minimal number of chargers that we need to install, along with these detailed charger schedule and charging profiles and like charger schedule profile from the beaker side and charger side, also with beaker battery profile. So once we determine how many chargers that we need to install at the depot, our next interest is to consider grid resilience side. So at this point, I'm considering grid peak shaping techniques. So the grid peak shaping is basically this essentially happens because once we start charging simultaneously right after bus operation ends, then most of the power demand will be focused on the starting time, and then it will be relieved over and over as this charging session ends. But by distributing charging sessions properly, then we might can keep this shape, and we might can shape this peak maybe from 150 to like 70 to 80. For now, this case this is only 160, but if you're considering like larger size fleet, then this goes up to higher numbers and might can affect grid resilience or grid stability as well. So that's our main motivation for this happening. So this one basically possible and distributing the charging session, and by how to this the way to distributing charging sessions is to put like either time before starting the next charging session. And so the main decision variable here is how many idle times to set up before starting the next charging session. And there should be some target function that we need to meet. And this case, the target function is to flatten the overall peak load. So for now, there is the target function which we define as a GT is a constant function. But I will cover this target function again in the later slide. And this the foundation of this the theoretical background of this technique is from the packing problem, which is pretty classic problem in OR or in combinatory optimization problem. So the goal of this like in-packing problem is to like how can we smartly set up the items within the like the beams that we have with the like the fixed capacity that we have. So this case actually is a variance or variance of these two in-packing problem. So I'd like to give you a brief like clues of like what are the theoretical background of these techniques. And essentially this is also an MPR problem. Then also I need to come up with some alternative algorithms. And for this case, I use top-approach algorithm for alternative approach. So once we solve this problem as a load flattening perspective, like starting from like this kind of power profile, and we can, after relieving this from the proper charging scheduling, and we can relieve this like as this kind of flattened shape. And there is one metric to measure the grid resilience, which is the load factor. So the definition of load factor is that there is a average power and there is a peak power, and it's a proportion of the average power to peak power is the load factor. So that means if this load factor is low, then there is a high gap between peak power and average power. So which means it's pretty hard, which is pretty danger in terms of grid stability. And if this load factor is high, that means there is a pretty less gap between average power and peak power, which means more stable. So by applying this like peak shaving, then we can relieve load factor about from like 80% to 90%, which can reduce like 8 to 12% of peak powers from this peak shaving algorithm. So, but at this point, I would like to mention another thing. So previously here, up to here, the main focus was to just flattening the low peak power. But in real world, as you know, the supply of the power or demand of the power is not a like constant function, or just flattening the power is not an right answer. Like as we can see from this data source, which is like RTU, which is the mid-Atlantic RTU supply and power supply and demand data. There is that it fluctuates over time and it highly depends on time. And here we define the interchange. We define this gap between supply of the power and demand of the power as an interchange. So which means if the interchange is the positive number and there is excessive power that we can utilize, and if it goes negative, then there might be some power shortage. So after collecting the data from the source and after pre-process, to be made in a ready to use format. I can see this kind of interchange. I can make this kind of interchange graph for our problem. And this is the monthly profile. But once we calibrate this again to like a daily profile, maybe just averaging it into daily basis, then we can finally come up with like adjusted target function, which I define as GT. So here, since we are interested in overnight charging policies, I only work from like 6 p.m. to 8 a.m. phases, and this adjusted function shows like how many interchange or how many accepted power that we can utilize for charge the fleet. So now our goal is to, instead of just flattening the peak load, I'm trying to fit this line another like adjusted like target function that we derive, and this is another peak shaving tactic that we can use. And actually, this might be more like realistic and practical approach rather than just flattening over the entire peak load. But this part is like still ongoing, and I also need to come up with some like proper metric to how these like to measure the efficiency of this technique. That's my another like task on my hand. So, and this is still in progress. So maybe I can conclude at this point. So this study, the third chapter, basically tries to examine like based on the electric, assuming the fleet electrification from like the school bus cases. We first come up with like what are the energy footprint or energy consumption footprint, and based on those profiles, we try to come up with what are the charging infrastructure requirements and how can we consider that resiliency from the charging scheduling perspective. And we can see some preliminary studies from the case study and in the future, and also this includes lots of implementation that we need to consider integration for chargers, or we need to consider like dynamic pricing for electricity, and we need to adjust in the peak shaving, elaborate this peak shaving tactic more. And also, as I mentioned, we need to come up with a metric to measure the efficiency of the algorithm. These are all like a piece of research that I'm interested in. I can conclude here, and thanks for attending the seminar for your. If you have any questions, I'm happy to answer.
I think condensing all the effort in 35 minutes or so was a good score. 40 minutes. Any questions on what June has done so far?
Thank you for the talk. That was really good. It's a general question about the temperature and meteorological conditions. Is that important in your calculations?
So in the
Winter, summer, hot, cold?
right. So that was one of the factors, as I mentioned, as the HVAC parts of the simulator, that thermal load is definitely considered under the electric bus simulator. And that definitely matters from the thermal load as an energy consumption. And from our research, we see the gap between like without considering those thermal load and weak thermal load is that there is gap up to like 30% from the energy consumption. So temperature for sure definitely matters for energy consumption for electric vehicles, and these are incorporated with the simulator aspect.
The outside air temperature, what you're talking about. Yeah.
But the first two researchers actually I didn't consider that kind of.
Okay.
There are two aspects. You look into the summer aspect of it or the winter aspect.
So it's basically
The summer aspect, right? Where you have to use the air conditioner.
I'm talking about the battery chemistry. The temperature, the outside air temperature, when it's really cold, does bad things to your battery. When you try to charge it. You know, we're talking about charging the batteries here, and yeah. So when it's like 20 below zero and you're out there at 2 o'clock in the morning, what do you do?
I don't think so. We have considered this, and given the scale of his problem, we're looking at the fleets,
Yeah,
looking at the battery. We are not there yet.
Okay.
We are still going down there. Yeah.
thank you.
So I have, and it was a great presentation, like so much overview, so much work that you've done, it's quite varied. So I have some questions about in the first part, minimizing fuel consumption. So there's that thing where you got 7,000 nodes from the image of the map. Did you automate that? Or was that
Sure, for processing.
data pre-processing?
Yeah, for sure, I cannot like manually processing like 7,000.
Did you develop code for that, or is there a module that will do this? Like you provide an image of a map and it'll give you the nodes and the edges?
So basically, I represent it as a visualized form, but essentially they are structured as a table like format, like with the starting node and you know, those are like structured as a node information or link information, and based on those graph network format, and we can like visualize or either use those for our research. So
So from here map, when you download that information, it gives you a table.
right, actually it's already very
It's a data that here API gives us.
Okay, I have some questions. So in the exact, like in the part where you talked about the combinatorial optimization takes time, so you develop the simulated annealing hybrid method. So you go from the solution where the charging is not considered to the case where charging is considered. So are you fixing the route for the agent or the truck, and then you are charging later? Is that how it is?
right. Actually, that's the like essence of two-phase approach. Like in the first phase, I basically come up with route planning without considering charging session. In the second phase, at that time I consider recharging planning. But as you know, that one of the main critical limitation of that kind of two-phase approach is like once we fix the route and once we change that one, it's not the optimal solution at all. So so that's why I like added few like modification, like adding some penalty terms that if there are effective situation in route planning session, in route planning phase, we can expect some like charging session, then we can adding those as a like penalty terms while we're considering route planning. So these are partially considered in the route phase.
Okay, so in the first phase, there's like a cost if you, so you basically do model the battery.
Right, yeah.
I think it's most relevant to what you are doing. So
I have a lot of questions, so I don't know. Okay. So for the queuing theory with the stochastic formulation, you basically you've showed the model formulation, but is there a solver that exists that can solve it efficiently?
So actually, the queuing theory is not a formulation or a equation that you can solve. It's a kind of stochastic modeling of the situation, the modeling of the charging station is that like based on the like if we have a certain arrival rate of the customers and we have a service rate for servers, then how can we model that as a stochastic perspective? Like what are the in terms of like probability, like how can we come up with probabilities or like expectations for like service time or waiting time? Those are like instance of queuing theory.
So then you just sample from that probability distribution, you get the parameters.
So it's not STEM. So those are definitely input parameters and input data that we use for those queuing models. But queuing theory or queuing model itself is aware of like the structure, is the model structure is there, and we can only like modify the inputs and input parameters and yeah.
But you're not doing stochastic programming.
So yeah, essentially I think essentially and for the output I'm not considering the true meaning of like uncertainty or stochastic programming.
going back to this question, what did we use to solve this problem? Was there any toolbox or any algorithm that was readily available?
No, actually, that's the another like a formulation that I proposed to solve the problem. And based on math formulation.
Math formulation.
So you put it through the Ruby.
Right.
I think you guys can keep on.
Yeah.
I don't see any questions online, so I think let's thank June. Thank you for the presentation.